Hi, this is Dr. Chin, and this is a video tutorial on how to conduct an exploratory factor analysis, complete with steps involved in screening and preparing the data set, including handling missing data, um, dealing with multivariate outliers, screening for multivariate normality, which is one of the assumptions that typically underlies common estimators such as maximum likelihood, as well as examining the correlation matrix um, to determine if there are sizable enough correlations for us to actually conduct an exploratory factor analysis. This video tutorial goes together with the example that we are using for PY557. Um, and so I hope that this video tutorial is helpful for going through the steps. Um, and I guess here goes nothing. So first of all, we want to have our studio open, which is a really nice interface for us to use in order to run analyses in R. First thing that we want to do is we want to open a new R Markdown file. So go to R Markdown under New File. I'm going to name this video tutorial. We want to output the output in Word when we knit the video all together. So I'm gonna go ahead and delete a lot of these stuff except for the first chunk over here. And you can see that the title is at the very top, including the author's name and the date, as well as the type of output. Now, if you're doing this for the assignment for PY557, what I would recommend is that you download the instructions or the grading rubric, really. Just right here, and copy all these sections to make sure that we cover all of our bases in regards to what needs to be dealt with. Now, we will be sort of going off on some tangents here and there as I just try to highlight some additional code that may be helpful for you to work with other types of data sets beyond just this assignment. Um, so if you're one of my students in PY557, for the assignment, you won't have to worry about missing data, for example. That is covered in another assignment where it'll just focus on data screening and preparation. But for this particular example, there is some missing data that we would need to deal with. And so we'll just go through the steps. So for those of you who are in my class, going through all the missing data handling procedures is probably a review for you, which is not a bad idea, especially if you're fairly new to this process of working with R and RStudio. So first thing we want to do is we want to import and view the data. So first step is to set the working directory. When we're setting the working directory here, you want to basically tailor the working directory to where you have saved the R Markdown file as well as the data file. As can be seen over here, even though I've created an R Markdown file with the title video tutorial example, it doesn't actually save it per se until I actually click Save Current Document. And I'm gonna save it in this particular folder. It's just called Discovery 413 because that's the classroom that we meet in. I'm gonna call this video tutorial example. Save that and notice how that title over here changes. Now, where this is essentially, and you actually see the RMD file right here, notice that this is in the same folder as the data set that I'm going to be using to demonstrate this EFA. And the name of the data set is EFA data practice. Our studio works best when the RMD file is in the same folder as your data file. So to figure out the path address for where this folder is located, so we can set the working directory, just right click on any of the files in this folder. And if you're using a Mac, it is get info. If it's Windows, then it's going to be properties once you right click. And under here, it's where. And I think under Windows, it is location as opposed to where. All right. So typically this will work. This works if we start out with users with Windows or Mac. Sometimes some people put a C drive into that path file. I don't think there's a need to do that over here. Notice that we need to use forward slashes as opposed to backward slashes, and we need to start and end with a forward slash. So if I copy and paste that into here, we also need to put in an open quotation marks and a closing quotation marks. Notice how the color changes when I do that. That's one of the neat things about our studio. It uses some color coding to help you understand what the program recognizes as legitimate code. So if you got that right, I just ran that code, and you can see in the console, typically if there are any types of errors, it shows up in the console. So I think we're pretty good in regards to that. Next step is to import the file into the global environment. We're going to add another chunk. And we are going to call this master data set. I'm going to use the read.csv function. And the name of the data set is actually EFA data practice. So I'm going to copy that, paste that name, and we're going to run that code. So according to the data set that's been imported into the global environment, this is a data set that contains 206 observations and 32 variables. Now, I typically like to double check that this is true. So if I open my data set in Excel, you should be able to see 32 columns of variables and 200 and it says here 207, but keep in mind in Excel, the first row is the header. So we actually have 206 observations with 32 variables. So Q1 all the way to Q32. And you want to make sure that your items are arranged in sequential order. This will help later on as we try to manipulate the data set and add or remove columns accordingly. So you want to double check that. I'm going to minimize that window. So we've imported the file into the global environment. I'm going to show you guys a couple of ways in which you could have a visual of the data. So we can use a summary function, not just to figure out how much missing data, but also to get descriptives. So we're going to just call this master because that's the data set that we imported into the global environment. And we see here that we have Q1 all the way to Q32. Most of the range of the data, it ranges from 1 through 7, which corresponds to the questionnaire from which this data set was obtained from. The questionnaire is actually here under EFA data practice scale.do.x. So this is a scale. It's based on this idea of self-determination theory. It's a theory of motivation that is concerned with supporting our natural or intrinsic tendency to behave in effective and healthy ways. So a scale was developed to assess why students are in college. And here we're going to test to see if those questions fit a factor structure that is consistent with that theory. The response options for each of these Likert type scales range from 0 through 7. Actually, this should be 1 through 7. So that's a typo right there. And the items range from 1 through 32. Notice here that I have a note saying that bolded items are reverse scored. So that is for item 6, 9, 17, and 27. I'll show you guys a code that you could use for reverse scoring that will work with most Likert style types of items. For the purpose of the assignment for PY557 though, one of the limitations of the data set that was generated based on the proposed factor structures that is individual to each student is that I wasn't able to have control over the mean intercepts. And so the range of the numbers actually range from, it's weird, it's from -3 to maybe +3 or something like that. The formula that we're gonna be using to reverse code the items, again, it works pretty well if your numbers are positive numbers. So anything from 0 and above may not work really well if you got negative numbers, but no worries. Your the functions that we're gonna use to run your EFA and to get estimates of your Convex alpha, which is the reliability for the subscales that we may come up with, they can recognize items that need to be reverse scored. So I'm going to show you the formula and how to reverse score if you are dealing with a normal regular data set. But just FYI, if you are one of my students in PY557, you wouldn't need to worry too much about having to reverse score. Okay, so we got the summary of that data set. We're going to use the view function to view the raw data. View, and remember, V needs to be capitalized. And it's just open close parentheses master. So that opens a new tab that shows you the actual data set as well as all 206 observations. Scroll too fast there. There you go. It just took some time for it to load. Keep going. There you go. Okay. And then we're going to use the names function to list variable names. So that's pretty easy as well. Just type in names, master. So that's a quick way for you to eyeball the variables that are in your data set and how they are arranged. Now, as mentioned before, if you wanted to reverse code items, and this is not relevant to the assignment per se, but for future purposes, I'm just going to say here, reverse code items. In this particular example, it is, what is it again? 6, 9, 17, and 27. So we are going to use this code. We're gonna refer to these specific columns by calling master and then open brackets space that's referring to all people or all rows, comma, and we want columns 6, 9, 17, and 27. And the formula over here is basically the maximum response choice for a Likert scale. In this case, it's 7. And you want to add 1 to that. So it's 7 plus 1, which is 8, minus the scores for, again, it's space representing all rows, comma. And we only want to do that for columns 6, 9, 17, and 27. Now, before I do that, one quick check that I typically like to do is to use the table function. And let's just extract one of the questions to see what the original distribution is. And then we'll compare this with the reverse score distribution. So if we made a table, for example, out of question 6 from your master data set, you see here that 104 put 1 as their response choice for question number 6. 41 people chose 2 as their ratings for question number 6. 21 chose 3. 15 people chose 4. 10 people chose 5. 7 people chose 6. And 8 people chose 7. Now, once we reverse score this, we should see the distribution be reflected, actually, or be inverted. So master $Q6. And so now, instead of 8 people having a response choice of 7. Now it's 8 people having a response choice of 1 for question 6, because 6 is just one of the items that we reverse score. And so this is just one quick way for you to double check that you did that the reverse scoring actually worked. Now let's go ahead and load relevant libraries for the EFA. Some libraries that you might could use would be Lattice. Another library that you could use is GPA rotation. And I think that might be it. Specific to an EFA. Now, if you've never installed Lattice or GPA rotation as libraries before, you could go ahead and do that by typing in install.packages, open parentheses, Lattice, between quotation marks, and do the same for GPA rotation. It will download that package from the CRAN server. I've already done that, so I'm just gonna go ahead and load the libraries. Same thing with GPA rotation. Let's see here. Another thing, I forgot about one more library. Another library that you'll need, especially to run the Barclay tests, to see if there are enough significant correlations in the correlation matrix, is the psych library. So I'm going to go ahead and load that as well. Now, as mentioned before, if you are a student in my PY 557 class, for your assignment, you will need to worry about missing data. But we do have some missing data in this example. So I'm going to go ahead and load the libraries that we need for that as well. So load relevant libraries for missing data analysis. We need mice. We need Baylor at psych. And we need MD and MLE. Okay. So I'm going to load all 3 libraries right there. Oops. Spell that. As well as Baylor at psych. Okay. So let's run a little MCAR test or MCAR test to determine what is the probability that missing data patterns is coming from a missing completely at random distribution. So run little MCAR test. Chunk here, and the function is little MCAR. You know, to do this on the master data set. And so the test is statistically significant. It is 0.11. And so we would retain the null hypothesis and say that missing data patterns appear to be missing completely at random. Now, in terms of the write-up, I'm just going to show you the write-up that I've written up over here already. We're in the second paragraph here in the write-up after describing the number of people in your data set as well as the instrument itself. So little test for MCR was not significant. 209 is the degrees of freedom, which is coming from right here. 234.06 is the chi-square value for this test, and P equals 0.11, which is coming from here, suggesting that the missing data pattern was missing completely at random. Okay, so missing completely at random is actually a good thing. That means that there's a really low chance, basically, of people missing or omitting their data because of how they score on that particular variable itself. So, okay. Next, we want to create a percent missing function, because notice over here, next in the write-up, I'm talking about the percentage of missing data according to participants. So how did we get that? First of all, we need to create a percent missing function. We're going to call this function percent missing function x, followed by, I can't really remember what's the name of that symbol, but it's not a bracket, it's not a parentheses. It's one of the other symbols that is on the same key as your brackets on your keyboard. You just need to press shift, or actually don't press shift. So sum is dot NA x, which is referring to that variable, divided by the length of x as well, multiplied by 100. So basically what we're doing is we're creating a generic function that is going to calculate the number of missing data points for any particular vector or variable, divide that by the number of total data points, regardless of whether you're missing or not, and multiply that by 100. And so that should give you a percent missing that you could apply across rows and across columns. All right. The next step is to apply the percent missing function to the data set. So we're going to apply that across rows first. So let's create an object called missing. We're going to apply on the master data set across rows, one meaning rows, the percent missing function. Okay. And we can create a table. So out of that, create a table out of that object that we just created. So the way in which you would interpret this is that the first row represents percentages, because that's what we had specified in line 67. And we're applying this across rows. So that means 197 people had 0% missing data, 8 people had 3.125% missing data, and 1 person had 28.125% missing data. So next thing you want to do is you want to include only participants with acceptable levels of missing data, which is 5% or less. Include participants with acceptable levels of missing data. I'm going to call this sub data set a replace people data set. Replace people equals to master, open brackets, and since we're applying this across rows, it's going to be missing less than or equal to 5, comma, followed by a space. That means that we are basically taking all the columns and putting that into the replace people data set. So if we did this right, remember only one person had more than 5% missing data. So in your replace people data set, now you should have 205 observations with 32 variables. And we also want to create another data set that has the participant with unacceptable levels of missing data. We're going to call this the don't people data set, in case you want to use this later to bind it all back together prior to running your analysis. Missing more than 5, apply this across rows, and space after the comma, meaning again, we're taking all the columns and transferring it to the don't people. So if we did this right, we should be able to see that the don't people data set has one observation, and that one observation is the one with more than 5% missing data. Next is to apply the percent missing function across columns. So it's very similar to this line of code over here, except we're going to name this object something different. Let's just call it missing2. And I'm going to put 2 over here, as in to apply the percent missing function across columns for the master data set. And if we create a table out of this object, we get some numbers over here. Now remember, because we applied this on columns, the numbers over here now represent the percent of missing data for for the number of variables. So 20 variables or 20 columns at 0% missing data, 8 variables at 0.48% missing data, 3 variables at 0.97% missing data, and 1 variable had 1.45% missing data. So we really don't have any columns that we would need to exclude because all the columns actually meet the criteria for acceptable levels of missing data. Now, if you, okay, so next step basically is to impute um, your replace people data set, the data set that contains people with acceptable levels of missing data. We want to impute that data set so that there are no missing data in there. So let's call this conduct, multiple imputation. You're going to call a set of data sets that you're going to produce, temp no miss, as in it's like a temporary placeholder for all the imputed data sets. Mice is the name of the function. It's actually pretty simple, given how complex the process is in terms of multiple imputation. So we are going to impute data in the replace people data set. It's going to give you 5 different types of data sets here. So 1, 2, 3, 4, 5. The next step is to select one of these data sets here, 1 through 5. So we're going to call this no miss, and we want to complete, and no miss, comma, and we can call this anything 1 through 5. So just pick a random number. We're just going to say this is 2. So we're extracting a complete data set from this set of 5 imputed data sets here. Specifically, we're going to go with the second data set, and we're going to call this no miss. If we check the summary for no miss, you'll find that we have no more missing data, as shown here. If there is any missing data, it'll come after the maximum value underneath each question. Now, contrast this with the original data set. Now, we previously had NAs for some of the items. Now, moving forward, what you could do is one or two things. I mean, given that, say if you wanted to put that one person who had more than 5% missing data back into your data set in order to analyze it, you could do that. And so let's just call this bind one person who had unacceptable levels of missing data back into the imputed data set. Code for this is really simple. Let's just call this new data set filled in complete. Code is rbind. So rbind represents binding rows. If it's cbind, that means they're binding columns. We would use the cbind function if we had excluded any columns with unacceptable levels of missing data. So rbind, we're gonna bind the columns, the rows of the no miss data set together with that one person, right? The don't people. So if you were to bind the no miss data set together with the don't people data set in terms of rows, we should get a new data set called filled incomplete that has 206 observations. And that's about what we get. Now in this case, it's only one person. I'm not going to worry too much about missing just this one person. In fact, actually the rest of the write-up and examples is based on the no miss data set as opposed to the filled incomplete. So I'm just going to go with the no miss data set to keep moving on in the next steps here. Because the next step after dealing with missing data is to identify multivariate outliers. So to do that, we want to create Mahalanobis values for every person in our no miss data set. And the code is mahal equals to mahal novus. Build in underscore complete. So that's not what the example write-up was based on. Let's use the nomis data set. All right, nomis data set, we are going to extract the column means. And we're going to do this column means. This code right here, na.rm, that means that we're only going to work with column means for those who have no missing data points. Again, with the nomis data set, this code right here is not needed. But in case if you decide to bind your data sets together, you could put this in. We're going to extract the covariance values, if that's part of the formula for calculating mahal novus values. Nomis is the data set, and we're going to use pairwise complete observations. That means we're going to use pairwise complete observations. Again, that is if you were to be using filled incomplete as your data set. So, oops, I think I misspelled something. Maybe it's that one. Let's try this again. Invalid use argument. Okay, let's see. Where did I go wrong here? I'll notice column. Find what is the random error here. So I'm going to copy and paste what I have here in the example and see where did I go wrong. Oh, I misspelled pair. Try that again. There you go. Fix it. Okay, so now every person in our nomis data set has a mahal novus value. If you want to get a summary of the mahal novus values, just go ahead and type in summary. Mahal. The mahal novus values range from 4.687 to 94.315. The mean is 31.844. Go ahead and calculate the cutoff score for p less than 0.01. So let's name this object cutoff. The function is QCHISQ. For p less than 0.01, that's 1 minus 0.001. Or we could also type in 0.99. Either one could work as long as you end up with the inverse of 0.001. So 1 minus 0.001. And columns that represents the degrees of freedom for calculating the chi-square value for this. The degrees of freedom is basically the number of items that you have in your data set. If you're curious as to what the cutoff is, just type in cutoff and run that code. Looks like the cutoff is 62.48722. Let's identify the number of people who exceed the cutoff. So that is summary, aha, less than cutoff. See how many people meet that criteria. 194 people meet that criteria and 11 don't meet that criteria. If everyone in your data set meets that criteria, this comes out as true and you don't really see a false column at all. So we need to remove these multivariate outliers then. Let's create a new data set called no out. And we only want those with mahal nobis less than the cutoff value, comma, space, which represents all columns. All right. So now in a no out, you have 194 people in there. That excludes the 11 people who were considered multivariate outliers. So now with that no out data set, let's go ahead and examine multivariate normality. First of all, we need to load the MV norm test package. Again, if you haven't installed it, you want to type in install.packages, followed by the name of the package. Let's transpose the data set. Make the rows be variables because that's how that package, that's what the package needs basically. Let's call this in transpose data set object M, and we're gonna do a pointy arrow. T is the name of the function, followed by no out, which is the name of your data set with no multivariate outliers. So when we transform this data set, we can now produce a multivariate normal QQ plot based on this transposed data set. And the function is QQ norm, and you just enter in the transposed data set. And here you go. So if your data set is coming from a multivariate normal distribution, the sample quantiles should correspond pretty well with your theoretical quantiles, giving you a nice diagonal line here. It looks like we are not, this doesn't really look like a diagonal to me. I think we probably are skewed in terms of its distribution. We can also plot a multivariate normal histogram. To do that, we need to load the R companion package. I guess we already have here. Take this away. Put in the code for loading the R companion package. That. And then use the multivariate normal histogram. So the name of the function is plot normal histogram no out probability equals to false. But if you put in false, your y-axis is going to be case counts. If you put in true, the y-axis is going to be probability densities. Either way, the shape is going to be about the same. And notice here that we are running this on the non-transposed data set as opposed to the transposed data set. So that's weird. Okay. Well, you can see over here that we are negatively skewed, with which most of the data piling up towards the upper end of the distribution right here. If you wanted to transform this, we would first need to reflect the variable before you put a square root or a logarithm transformation. If this was positively skewed, meaning that the data was piled up towards the left, you don't need to reflect the variable. You could just go ahead with the transformation. Again, for the assignment data set, I don't think um, the formula for reflecting the variables is going to work with the cells that have negative values. So I wouldn't really worry too much about trying to transform your data set, especially if you need to reflect your variables right here. But I'm just going to go ahead and show you how to do it if this was a regular, Likert scale with response choices that are from 0 and all other positive numbers, like 1 through 7, for example. So let's see if we could, first of all, reflect the variables so we can use the square root transformation in an attempt to make the distribution more multivariate normal here. Because data is negatively skewed, need to flag the data prior to transformation. Formula is basically the maximum value of your response choice in your scale. In this case, it's 7 plus 1 minus the values of each variable. So in this case, let's call this no out underscore reflect, and it is going to be 8 minus no out. So basically, turn everything the opposite. And then the next step would be to apply the transformation. A square root transformation is less extreme compared to a log transformation. So we're going to do a square root transformation first. So apply square root transformation to reflect the data set. Call this SQRT, no out underscore reflect. The function here is SQRT, no out underscore reflect. So basically, we're doing a square root transformation on your no out reflect data set, and we're going to call this new data set square root no out reflect. Next, we're going to transpose this transform data set. Because the QQ plots require the rows to be variables. So let's call this square root M underscore reflect. And the function here is t. I'm going to apply this to the square root t underscore no out underscore reflect. Okay. Then you're going to produce the multivariate normal QQ plot. It is QQ norm, QQ norm, and the data set that has been transposed to square root M underscore reflect. See how we're doing in terms of the QQ plot. I don't know, it doesn't seem like there is a straight diagonal line here as well. So it doesn't seem to be corresponding really well with the theoretical quantiles. Let's plot the multivariate normality histogram. So function is plot normal histogram, and the data set is the square root underscore no out underscore reflect. Probability is false because we want case counts. And it looks like we kind of went the other way. So now instead of being negatively skewed, now we're positively skewed which isn't exactly what we want as well. In this case, I wouldn't even try a log or an inverse transformation because it's just going to make it even more extreme. So we're just going to proceed with the next steps in the analysis with the non-transformed values. We're going to use an estimator called weighted least squares because weighted least squares is more robust towards violations of multivariate normality compared to maximum likelihood. So I have a brief explanation of this written up over here. In the interest of time, I'm just going to copy and paste that. So because the square root transformation made the distribution positively skewed instead of being normally distributed, we will proceed with next steps in the analysis with the non-transformed original values in the sample data set to basically preserve the interpretability of the parameter estimates. We will use weighted least squares as an estimator for subsequent factor analytic procedures, which is an estimator that is robust towards violations of multivariate normality. So back to the write-up over here. And I apologize, I missed coming back again to the write-up. Just to show you guys again where these numbers came from, talking about missing data. Participants with 28 point, oh, hold on, right here. This is coming from when we had applied the percent missing function across rows, which is right here. Right here. So 8 people with 3.125% missing data and 1 person with 28.125% missing data. That's what we have written over here. The participant with the 28.13% missing data was discarded, like what we talked about before, leaving us with a total sample of 205 individuals. This whole LURP here is talking about what multiple imputation is, and if we use mice the way in which we used it in our analysis, in our multiple imputation. So, yeah, if you use it this way, basically all the variables in your data set are used as predictors to try to impute the data for multiple imputation. When we calculated Mahalanobis values, a total of 11 participants were identified as multivariate outliers. So that's coming from this one right here. So 11 participants were considered multivariate outliers. The cutoff value is coming from this code right here. (62.487) based on p less than 0.001 and degrees of freedom equivalent to the number of items. So 32, 62.49 in terms of the chi-square, and p equals to 0.001 is that cutoff. These 11 participants were discarded, leaving a total sample size of 194. Then we get to the multivariate inspection. Visual inspection of the multivariate QQ plot and histogram suggested that the variables were negatively skewed, as shown here. Okay. A square root transformation of reflected variables yielded a distribution that was positively skewed instead. So that is referring to this. Now we've gone to the other end of the distribution, which is not what we want. Because this transformation did not yield a multivariate normal distribution, the subsequent exploratory factor analytic steps will use weighted least squares as an estimator because weighted least squares is robust towards violations of multivariate normality. So that's basically a summary of what we wrote here. So let's actually do some pre-analysis prior to conducting the EFA after we've dealt with all of that stuff in regards to multivariate normality, multivariate outliers, as well as missing data. So first of all, before we conduct an EFA, we want to determine if there are enough significant correlations to run a factor analysis. So first of all, we need to create a correlation matrix of variables that we can run the test on. We create the correlation of variables. We name this object correl equals to CUR is the function representing correlation for the NOAA data set. And in case if you do have missing data over here, you want to add in pairwise.complete.ops. So now you have a matrix of correlations for you to run your Barclay test on that correlation matrix. To run that test, it's as simple as typing in cortest.drtlett on the correlation matrix, and n equals to the number of rows in your no-on data set. Okay? So the value is actually p less than 0.001 with a chi-square value of 4773.05 with 496 as the degrees of freedom. So that's going to be written in here as the Barclay test suggested that the correlation matrix was not an identity matrix. An identity matrix is basically a matrix where the diagonals are ones and all the off diagonals are zeros, meaning that there's no correlation between the variables. And we want to see what is the probability that our correlation matrix is coming from that identity matrix. And it turns out that's a super low probability, you know, p less than 0.01, that our correlation matrix is an identity matrix. So that's good news so far. We want to be able to reject the null. So the interpretation is going to be this right here. Another thing that we can do is that we can run the Kaiser-Mayer-Alkin test. This is basically a ratio of the sum of squared correlations divided by the sum of squared correlations plus the sum of squared correlations. This index ranges from 0 through 1. And they can be interpreted with these guidelines right here. Just gonna copy and paste this. In your overall MSA value, anything that is above 0.5 is what is considered acceptable, although you probably want something closer to 0.8 or above. So strive to have an overall MSA value of above 0.50 before proceeding with your EFA. If the MSA values falls below 0.5, then you can look at the variable-specific MSA values to identify what variables you need to delete to achieve an overall value of 0.50. So the code for that is surprisingly simple. It is KMO, all capitalized, and you will apply that to the correlation matrix that we've been analyzing so far. And it gives you the overall MSA value, which is 0.92, which is good, actually, suggesting that we do have sizable correlations in our correlation matrix to warrant doing an exploratory factor analysis. The difference between the Barclay test of significance versus the KMO value, think about the Barclay test as a statistical significance test. And think about the KMO values as effect sizes. And so we want to have a statistically significant result so that we can reject the null hypothesis and to be able to have sufficient sizable correlations for us to say that, yeah, I think it's reasonable to assume that there may be 1 or 2 or maybe more latent factors underlying our variance covariance matrix. So the interpretation is written over here. The overall Kaiser-Mayer-Alkin measure of sampling adequacy was 0.92, suggesting that the sample correlation matrix had sufficient intercorrelations among the variables to warrant conducting an exploratory factor analysis. I think I did mess up something there. There you go. Actually, I don't need a chunk for that. I know why I did that. Okay. Now, let's determine how many factors that we can extract over here. We can make a scree plot and we can conduct a parallel analysis. And just as like what we discussed in class, a scree plot is basically a visual examination of where the slope of your eigenvalues plotted against the number of factors, where the slope changes. A parallel analysis basically superimposes eigenvalues that are obtained from basically a data set filled with random numbers. So to make a scree plot and to do a parallel analysis together, you can just type in this code. Let's call this object number of factors, so no factors equals to fa.parallel. That's the name of the function. On your NILWA data set, and the estimator is going to be weight of least squares. If it's maximum likelihood, then it's going to be ML. And FA is going to be the type of data reduction technique that we're doing over here. So FA stands for factor analysis. Okay, so this is the scree plot. Again, x-axis, the y-axis represents the eigenvalues, which is the sum of the variance of each of the indicators that load onto that factor. And we want a factor to, at the very least, be able to account for more than the variance that is accounted for by a single indicator. So in an exploratory factor analysis, the variance for the indicator is standardized at 1. So that's sort of our benchmark right there. If you have any factors that have an eigenvalue of less than 1, that means that factor sounds like it's only able to explain what seems to be less than 1 indicator. So, why would you want to extract a factor that has little explanatory power? The blue line represents the eigenvalues coming from your data set plotted against the factor number. The red line represents the eigenvalues coming from simulated data. Basically, this data is basically a random set of numbers. And the idea is that you want to only extract factors that have eigenvalues more than the eigenvalues that you could otherwise generate from a random set of numbers. In this case, it looks like maybe 3 factors would be a reasonable number of factors for you to extract based on the parallel analysis results. You could also look at where the slope changes. And so you can maybe make the argument that the slope changes between the 3rd or 4th, or between the 4th and 5th eigenvalues. I would say the 3rd and 4th would be where the slope significantly changes right there. So far, the interpretation of a parallel analysis is that, 3 factors appear to have eigenvalues higher than eigenvalues generated from a data set filled with random numbers. We also say the scree test suggests that slope changes significantly between factor 3 and factor 4. Suggesting, let's say that. This means extracting 3 factors may be a reasonable number of factors to extract. Now, you may recall us talking about the Kaiser Gutman rule. And again, the whole idea is we only want to extract factors that have eigenvalues more than 1. To get a quick read on that, we could use this formula right here. So sum for the no factors object. We're going to extract the FA on values that are more than 1.0. So how many factors basically have eigenvalues more than 1.0? It is 3, as is suggested over here. If you wanted to do, if you want to extract factors based on eigenvalues more than 0.70, same formula, except it is 0.7. So also 3. So based on the aforementioned and theoretical rationale, provide a reasonable explanation for extracting X number of factors. Here you can say results from the parallel analysis, scree tests, as well as the Kaiser Gutman rule suggests extracting 3 factors. So they all appear to be apparently consistent in this regard. So let's extract 3 factors. Let's actually run an exploratory factor analysis. So the first attempt at our EFA is going to be this. We're going to call this first round, round 1. FA is the function for the factor analysis on the NOAA data set. We want to extract 3 factors. The rotation that we're going to use is Ableman, which is one type of an oblique rotation in order to achieve simple structure. And the estimator is going to be weighted least squares. Now, when we extract the results over here, I want us to copy and paste the factor correlations between factors 1, 2, and 3, just so that we can get an idea of how well our factors are correlating or not correlating with each other. This can help sometimes if you're kind of iffy on whether you should extract, 2 factors or 3 factors. So that can give us some clues. And I want us to copy and paste the standardized factor loadings from here. And copy this into an Excel sheet, essentially. I'm going to open an Excel sheet, a new Excel sheet. We're going to call this maybe let's see here. I need to go to my courses, 2020, EFA, example, study for 13. Call this EFA factor loadings video tutorial. Okay. So there are some nifty tricks over here that you can do in Excel to make your life easier. So first we are going to copy and paste all those factor loadings. Notice that the data is not arranged in columns. In order to arrange those in columns, you want to click on data and click on text to columns. It does a pretty good job generally of recognizing like what is what, especially when it comes to numbers. So I typically just click finish. And so we have here the standardized factor loadings for factor 1, 2, factors 1, 2, and 3. We're going to remove these columns right here because they refer to other indices such as commonalities. We're not going to worry about that. Let's change this from Q1 to Q32 to actual numbers because it'll be easier for us to sort and resort the data. One easy way is for you to start a sequence and then click on the bottom right corner of Excel, drag it all the way down to the bottom, and it'll basically create a sequence of numbers for you. Now, the other thing that we should also copy and paste here are the factor correlations. Let's put that over here. Again, go to data, text to columns. Let's name this F1, F2, F3, F1, F2. Same thing over here. One, two. Now to help us figure out what are these specific items that load onto specific factors beyond just these numbers, I would go ahead and copy and paste the actual items themselves into Excel as well. So we can actually see what what wording goes with what factor loading. So many windows. There we go. Remember, the bolded items are the ones that are reverse coded. Have an opposite valence compared to everyone else. Okay, let's tidy this up a little bit. Put some borders. Where are my borders? There you go. All borders. Perfect. Now we're going to sort our factor loadings from low factor loadings to high factor loadings so that we can highlight those that meet the criteria of 0.3 and above. And you can do this with standardized factor loadings because the value of standardized factor loadings is standardized. It doesn't go above 1 or negative 1. So select all of your data and then click your data and then click the sort A to Z function. You can sort this from smallest to largest or from largest to smallest. It's up to you. It'll ask you if you want to expand this selection. Go ahead and do that. Basically what it will do is it will also change the values in the other column or sort the values in the other columns according to how you're sorting that particular column. So we're able to keep the data from each item in the same row. So there's actually a bunch of items here that load onto factor 1. You want to also watch out for any factor loadings that may be negative and more than 0.03. So like negative 0.35, for example, that would be the opposite factor loading. Let's sort the factor loadings for the second factor. Expand. And sort that. I'm going to highlight that accordingly. Let's do the third factor. Oops, what am I doing? Sort it first. Okay. Now if you sort this back according to the items, the data, and sort this. If you wanted to put this back on top, you copy and perhaps insert cut cells. There you go. Okay. So if you look at the items for factor 1, stuff such as the reason why I'm in college, because I experienced the pleasure and satisfaction while learning new things, or to show to myself that I can succeed in college studies, or because it's one of the ways in which I've chosen to acquire skills in an area which is important to me, or for the pleasure I experienced while surpassing myself in my studies, or for the intense feeling I experience when I'm communicating my own ideas to others. These items, I think, appear to map onto intrinsic motivators for staying in college. If you look at factor number 2, this corresponds to I wonder what I'm doing. I actually find it really boring. Honestly, I don't know. I truly have the impression of wasting my time. I don't know. I can't understand what I'm doing. And once I had good reasons for registering in college, but now I wonder whether I should continue. This here refers to either ambivalence or disorientation. Notice that it also corresponds to all the negatively worded items. Unfortunately, with an exploratory factor analysis, it is limited in the sense that we aren't able to model method effects. Um, we did talk about in class about how it may be more severe to under factor, as in to extract too little factors compared to over factoring. So in this example, I'm kind of leaning towards still extracting this as a separate factor. It remains to be seen how this might look like in a CFA if we were to actually explicitly model a method factor or would put um, covariances between the error variances of each items. But given that we're just dealing with an EFA right now, we will probably, actually, hold on. It does look like we have other items here that that also load onto this factor. The problem is though, is that these items here are loading onto more than one factor. Um, okay, we'll come back again to this. If we were to exclude all the items that, cross load, I think we are still left with the reverse coded items. Okay, moving on to factor 3. Item 2 says, because I'm here in college because I need to get a degree to get a good job, because college provides me with a better understanding of the profession which will be mine. I needed to complete my degree. Um, it's a prerequisite. So it kind of feels like factor number 3 is mapping on to perhaps the instrumentality or practical reasons as to why we're in college, to get a good job, to get a degree, as opposed to something that is more intrinsic. Let's take a look at the factor correlations over here as well. Typically, if we are concerned that we are extracting too many factors, we could also look to see if the factor that we are feeling iffy about extracting, if it's correlating too high with the other factors, typically 0.85 and above in terms of a factor intercorrelation. Say, for example, if factor 2 had a factor correlation with factor number 3 of 0.90 as opposed to a zero point 0.2, then it's going to be really hard for us to make the argument that factor 2 and factor 3 truly are different factors because they have such a high correlation. So just eyeballing the factor correlations here, it does look like the factors, I mean, they are correlated, but not super correlated for us to be concerned that any of these factors might actually be the same factor itself. So all that being said, I think we're probably going to extract 3 factors, but we also need to weed out questions that are cross-loading on 2 or more factors because we need to achieve simple structure. We only want one item to load onto one factor. We also want factors to have at least 3 or more items each, because that has got to do with computation and convergence issues, which we'll talk about later when we discuss CFAs. And we also want to remove any items that are not loading onto any of the factors. So let's take a closer look at the items here. So it looks like we got item 11 and 12 cross-loading. So I'm gonna mark that as red. We've got item 15 cross-loading as well on all 3 factors actually, even after rotation. Are there any other cross-loading items? I don't see any other cross-loading items over here. So For part B in the grading rubric, just submit the Excel sheet that you created that has the factor correlations and the standardized factor loadings. By the way, let's call this first set of factor loadings round 1, just like how we named it in our studio. Part C is the interpretation of results based on the aforementioned information and theory. So I might say something along the lines of items 11, 11, 12, and 15 are cross-loading on 2 or more factors. Although factor 2 appears to consist of items that are reverse coded, suggesting the possibility of a method effect pretty much masquerading as a real latent factor related to self-determination theory, because that's where the scale is coming from. When the person made this scale, they had self-determination theory as the overall framework. So although factor 2 appears to consist of items that are all reverse coded, the correlations among factors 1, 2, and 3 appear to be low enough for us to not be worried about the discriminant of these 3 factors. In your assignment, if you can also come up with other good reasons as to why you feel like it's reasonable to extract, say, a factor that appears to only consist of negatively worded items, let me know that. I'll be curious to hear what your rationale is. You always want to provide an explanation that is defensible, that is reasonable. Because ultimately, the best way for you to really figure out if your scale truly is measuring what it claims to measure, we need some external criteria beyond just the instrument itself. For the purposes of PY 557, we only have time to talk about doing an EFA and a CFA. We don't have time to talk about how would you actually mount the study that might include other external criterion as well. But ultimately, that'll be how you would have more confidence that whatever factors that you're extracting truly is a latent factor and not just a coming from a method effect. Okay, so what we're gonna do in the next round, I think, is we're going to rerun the factor analysis without items 11, 12, and 15. So let's see here. Let's call this A.1. Run second attempt at EFA. Let's copy and paste the code right here. Let's call this round 2. And we want to exclude columns 11, 12, and 15 because they corresponds to items 11, 12, and 15. Okay? That. Oops, did something wrong. Minus columns 11, 12, 15. Oh, I know why. I put a period as opposed to a comma. Let's try that again. All right, there you go. Round 2. So let's open another tab in the Excel sheet. Let's copy and paste the factor correlations again. Right there. We can copy and paste the items, but we want to be, oh, hold on. let's copy and paste the factor loadings first. Oops. This. Let's put text to columns. So the data is in their respective columns. Let's only retain the standardized factor loadings. Let's see if this still works. We still do text to columns. There you go. We're still able to do that. Now notice in here that we no longer have items 11. So we're jumping from 10 to 13 because we're excluding items 11, 12, and 15. So if you created your own numbering system here, you need to change this accordingly. 15. So this goes here, and this goes there, followed by 30, 31, and 32. This one. Factors 1, 2, 3. Factor 1, and if you want to put in the items as well, you can do this, except let's exclude the items that are in red. So you want to be really careful when you copy and paste your items here. So make sure that they still correspond to your item numbering. Okay. Let's make this a little bit more presentable. Let's add some borders. Same thing over here. Okay. Now, let's go ahead and sort this data so we can highlight the salient loadings. Okay. This one. Sort this. Looks like we do have another cross loading. Okay. Sort this back based on the items, which is not so confusing. Sorry about that. Am I still recording? I am still recording. Okay. Still sharing the screen though. Sorry about that. Accidentally clicked on stop share. Okay. Go ahead and data sort it. Okay. Go to the very top. All right. So F1. Because I experience pleasure and satisfaction, to show to myself that I can succeed in college studies. This is one of the ways I've chosen to acquire skills for the pleasure I experience. And so factor 1 is still the intrinsic motivations to stay in college. F2 is covering because I need a degree to get a job. Actually, let's go ahead and remove the cross-loading items here. We can have a battery of relevant items. Are there any other cross-loading items? Looks like that's the only one. Okay, so factor 2 has because I need a degree to get a job, because college provides me with a better understanding of the profession, because I have to go to college in order to get my degree. It is a prerequisite to getting a job that I want. So F2 appears to be referring to the instrumentality of staying in college. And F3 appears to be the ambivalence confusion factor, it looks like. And we have at least 4 factors, which works out. If you do have one factor that only has, say, 2 items, I would remove that factor altogether. Um, okay, let's look at the factor correlations here. I don't think we have any concerns here about having any factors that are correlating too high with each other. Um, the correlations here suggest that we do have some degree of discriminability, although the best way to find that out, again, is to actually correlate these factors with some external criteria, which is beyond the scope of what you're trying to do here with the EFA. Let's call this round 2. So we are going to go ahead and remove item number 4 in the third round of the EFA. A.2 run second attempt at EFA. On this round 3, oops, not second attempt, third attempt. So now we want to exclude lines 4, 11, 12, and 15. Everything else should stay the same here. All right, let's make a new tab. Correlations are this one right here. Let's do text to columns. Step standardized factor loadings. Text to columns as well. And we retain the standardized factor loadings. All right. So this is 1, 2, 3, 5, 6, 7, 8, 9, 10, 13, 14, 16, 17, 18. I think that should be everything else. So we can do this. Let's put down 17, 18, 19, 20, all the way to 32. So let's double check. 1, 2, 3, 5, 6, 7, 8, 9, 10, 13, 14, 16, 17, 18, and so on and so forth. All right. Now for the items, we want to only copy the ones that are not in red. So 1, 2, 3. Everything else should be the same, I think. 7, 12, 15. Okay. Okay. Borders over here too. And all this 1, 2, 3, sort the data. I like that. So the next chapter. Okay. And so this next chapter. And let's sort the items back again. Back up here. So, do we have any cross-loading data? Take a look. So we don't. Do we have any items that are not loading onto anything? Don't. Are all factors consisting of 3 or more items? Looks like that's good as well. So factor 1, this refers to intrinsic reasons for staying in college. Factor 2 appears to be ambivalence or a lack of direction. Factor 3 appears to be instrumental reasons for being in college. If you look into factor correlations, we do appear to have sufficient discriminant validity, tentatively at least, from just looking at the factor correlation. So in the write-up, this would be basically how one could describe it. So first of all, after testing all 32 questions, the 3 items, 11, 12, and 15, cross-loaded across several factors, using the criterion that standardized loadings must be greater than 0.30. These items were eliminated from further analysis. Then in the second step, a revised 3-factor model was tested with this 29-item measure. In this measure, one item, which is item 4, cross-loaded across 2 factors using the criterion that standardized loadings must be greater than 0.30. These items, this item was, that's what I meant to write here, was eliminated from further analysis. And finally, a revised 3-factor model was tested with this 28-item measure. This model achieves simple structure with each item loading on one and only one factor. Factor 1 included 17 items that measured the intrinsic motivation of attending college with questions such as, and you would include maybe 2 or 3 examples. Factor 2 included 7 items that appear to assess instrumental reasons for being in college, such as, and you would include some example items. Factor 3 included 4 items that appear to assess confusion or disillusionment with college, including, and you provide some examples in there. And if you're writing this in an APA paper, the questionnaire will be in the appendix, and the tables would be the factor loadings as suggested over here in the write-up. The reliability of all 3 factors range from excellent to good. So we'll talk about that in just a little bit. But before we move on, I do want to say for the assignment, don't worry about making a table or making the tables in Word. Basically, I only need 2 things from you. I only need the R Markdown document, which is knitted together. And I would also want the Excel sheet that contains basically your factor loadings and the items, basically the results from your rounds of EFA. You may only need 1 round of EFA, of an EFA to get a clear result. Maybe it's 2, maybe it's 3, maybe it's a little bit more. You're probably not gonna go more than 5, I don't think. Again, with EFA, this really is an exploratory phase of the data reduction process. So it's not uncommon for people to do the EFA, look at the results, redo it again, look at the results until you achieve basically simple structure. Okay. So next we want to calculate the reliability of the final factor score. And I know that, in class we talked about some of the advantages and limitations of convex alpha. So I'll just show you guys how to get convex alpha. First of all, we need to create factor scores based on this theoretical model. And so basically, you would just do this. And admittedly, these are coarse factor scores. They're not really nuanced in the sense that they don't take into consideration that some of the items have stronger or weaker loadings on the factors. But again, just as a quick and dirty way of getting a sense of reliability, first we create the factor scores, then we run the convex alpha. So to create the factor score, say factor 1, this equals to columns, and what was it? In the this included factors. I still can't see it. Let's zoom in. Tell you what. I have a small computer screen, so I gotta get a little bit creative over here. Let's view. Let's freeze the first column. Let's zoom in. Oh, let's really zoom in. Do that. There we go. There you go. Okay. So factor 1 has columns items 1, 3, 7, 8, 10, 14, 16, 18, 20, 21 through 25, 29, 31, and 32. 29, 31, and 32. But that should be how many items again? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it's 1, 3, 7, 8, 10, 14, 16, 18, 20, 25, 29, 31, 32. Perfect. All right. Factor 2 equals to items 6 and 9, 17 and 27. And factor 3 5, 13, 5, 13, 19, 26, 6, 28, and 30. So again, it's 2, 5, 13, 19, 26, 28, and 30. Okay. So let's run that. So now we got the factor scores. Next is to run the convex alpha calculation. It is basically sec 2 colons alpha on the no-out dataset for all rows, but we only want for factor 1 as we calculated here at the very top. We're going to do check.keys equals true. Basically, this means the computer is going to check to see if items need to be reverse scored. If they do, then they'll just reverse score it for you automatically. This will be factor 1. And we'll do the same for factor 2 and factor 3. Okay, so run the first one. So what you want to get is you want to report the, I would like to report the raw alpha because as we talked about in Develis, the formula that goes into calculating the raw alpha, it tends to preserve the weightings of the items a little bit better compared to the standardized alpha. But really, for the most part, both of them will typically give you about the same value of convex alpha either way. And you also want to report your alpha together with the lower and upper limits in terms of your 95% confidence interval. So the 95 confidence interval is 0.93 to 0.95. So the reliability of, well, I guess in this case, we're talking about all 3 factors. And so before we go into that, basically, let's save that. Convex alpha for factor 1 is 0.94, and the 95% confidence interval is 0.93 to 0.94. And if we ran the convex alpha for the second factor, try this again. All right. For the second factor, the convex alpha for factor 2 is 0.9. 95% confidence interval of 0.88 to 0.92. Run the code for the third factor. Convex alpha for factor 3 is 0.86. Going with the raw alpha here, with a 95% confidence interval of 0.83 to 0.89. So that's the reason why in the write-up, I mentioned here that the reliability of all 3 factors ranged from excellent to good. We're going to use the interpretation guidelines given here by Develis. Here, let me just say, interpretation guidelines from Develis. So our lowest really is 0.86, and even if we were to take into consideration the lower limit of the 95% confidence interval, we're still in the very good phase over here. In fact, for developers, they say that anything that's above 0.90, you could consider shortening the scale. We're not going to worry about that. I mean, suffice to say that the convex alpha, the reliability index for all 3 factors is pretty good. So I say here that the reliability range from excellent to good with these numbers here that correspond to factors 1, 2, and 3 respectively. So that's pretty much the entire example for the EFA assignment. Once you're done, you would go ahead and then knit the document and submit that R markdown together with the Excel sheet, so that I can have a better visual of how you make sense of your factor loadings as you did your EFA. So I hope this was helpful. Let me know if and when you run into issues or problems or questions. And I hope that this will be a good learning experience for everyone who does this. That is all, and take care, and I'll talk to you soon.